We are in Unit 11, and this is notes number 5, so this is our day 5. Today we're doing our next test in our test for convergence and divergence of series. This is called the alternating series test. So I would like to start off by just taking a look at what an alternating series is. Okay, so let's take a look at something that we're already familiar with. We did this last time we were together. Let's take a look at this series. We have the sum of 1 over n, and if we write out some terms of that, the first term would be 1 over 1, second term 1 over 2, 1 over 3, 1 over 4, and we proved last time that this diverged. This is a diverging p series. This is our diverging harmonic series. We proved it because we did the integral test on it, and the integral diverged, so the sum diverges, right? So we knew a little bit about this. I'd like to look at this a little bit of a different way. Let's look at this on a number line. Let's say we have a number line, and remember back when we first started convergence of series, we said that a series converges if its sequence of partial sums converges. A series diverges if its sequence of partial sums diverges, right? So let's think of the partial sums. And when we did this before, we did s sub 1 is equal to 1. S sub 2 is equal to the sum of the first two terms, etc. Let's take a look at that on a number line. The first sum would be out at 1. Right? So we'd be here at 1. The second partial sum would be 1.5. So we would go from 1 and we would add a half, right? So let's say that 0 is out here. So adding a half would take us to like somewhere around here. And then we would be at 1.5. And then we would add a third. So let's add a third. So we're adding a third. And then we would add a fourth. So we'll add a fourth. Then we would add a fifth, and then we would add a sixth, and we'd add a seventh, and an eighth, and a ninth, and a 10th, and eventually we're adding very tiny things, and it looks like we're slowing down. We're slowing way, way down, but obviously, because I know this diverged, we're not slowing down quickly enough. So it's going to keep on going to infinity, okay? That's where we've been. Right? Now, let's take a look at this series. All right, let's take a look at this one. What's the first term in this series? Well, when n is 1, we'll have negative 1 squared, which is 1 over 1. So 1 over 1 again. We're back to 1. Okay? Our next term, when n is 2, we'll have negative 1 cubed, which is negative 1 to an odd power, so it's a negative 1. So negative 1 over 2. Our next term will be back to positive 1, and it's going to be over 3, minus 1 over 4, plus dot, dot, dot. Okay? This is an alternating series. An alternating series is a series whose terms alternate in sign. That's all an alternating series is. So this is an alternating series because the terms alternate in sign. Lots of times we can tell it's going to alternate by this negative 1 to this kind of an n power. Okay? Let's take a look at what happens to this one on a number line. Let's say we start out here at 1, right? So I'm going to move my 1 over here this time. I'm out at 1. My first partial sum is 1, right? Then I'm going to subtract a half. I'm going to make 0 over here. So then I'm going to subtract a half. So I'm subtracting a half, so now I'm here. Then I'm going to add a third. So I'm going to add a third. So maybe I'm out to there. Then I'm going to subtract a fourth. I'm going to subtract a fourth, add a fifth, subtract a sixth, add a seventh, subtract an eighth, this thing is going to converge. And it's going to converge to somewhere around there, wherever that is. But it is going to converge. I know it is. Okay? This alternating series converges. And here's why. It converges because, the series converges because it is alternating in sign, and the terms are decreasing in magnitude or in absolute value. It's decreasing in magnitude. Not only is it decreasing in magnitude, but the limit is 0. As n goes to infinity. Whenever that happens, your alternating series is going to converge. So, if the terms are decreasing in magnitude, so a half is less than 1, a third is less than a half, a fourth is less than a third, if they're decreasing in magnitude and going to 0, so the limit is going to 0, then your alternating series is going to converge. And I think that this is a great visual of what's happening. Okay? Not only is it going to 0, or not only is it converging, but what's it converging to? Well, if this first term is positive, the first thing that's being taken away from it is going to be the biggest thing taken away, right? And then you're going to add a small amount and then take away a smaller amount and so forth. So not only is it converging, but it's always, your answer is always going to be, it's going to converge to something less than that first number if it's positive. What if our first number was negative? Well, if our first number was negative, whatever it is, negative whatever it is, then the next number would be positive. So you'd be going like that. And then you'd be going back a little bit and forward a little bit, back a little bit, forward a little bit, back a little bit, forward a little bit. So your answer would be bigger than that number if it was negative. If it starts negative, your answer will always be a little bit larger. It will be larger than that value. If it starts positive, though, it will converge to something a little bit less than that. Okay? All right. So that's really all an alternating series test is doing. Now, what if I can give you another alternating series? What if we had that? What would the terms of this one be? Well, we would start positive, and then so we'd start at 1, minus 2, plus 3, minus 4, plus 5. That's alternating, isn't it? It is alternating, but it's not decreasing in magnitude. It's increasing in magnitude. So what would that be doing? Well, we'd still start at 1, and then you'd subtract 2, and then you'd add 3. Then you subtract 4 and add 5. Then you subtract 6 and add 7. That's not going to converge. Okay? So if it's not decreasing in magnitude to 0, your alternating series cannot converge. It has to diverge. Okay? All right. So that's what the first part of this little intro says. Okay? If your series, usually if a series is not alternating, just knowing that limit is 0, it really doesn't tell us that much. But if your series is alternating and the terms are decreasing in magnitude to 0, then your series converges. That's the alternating series test. You can say it in words. You can say it in words, or you can say it mathematically as a test. All right? Okay. Be careful with this, because the alternating series test can only be used to prove convergence. your series will never diverge by alternating series test. If that limit is not 0, then the series diverges by nth term test, not by alternating series test. Okay? All right. Let's do some examples. Here we have a series. It is indeed alternating. I know it's alternating because of that n+1 exponent on the -1. So it is alternating. That's the first thing I check. So if it's alternating, let's use the alternating series test. We are going to get 2 more tests that we can also use for an alternating series, that are good for an alternating series. But we haven't gotten there yet, so we're going to use the alternating series test. So the first thing I look for is it alternating? A lot of times students like for me to do a 1, 2, 3 test. Is it alternating? It's alternating. Check. We're good. Step 2. I like to do this limit in the next one, the next step. Okay, so I'm taking the limit as n approaches infinity, and I don't care about the -1. You can ignore the -1. You can put the -1 in if you want to, but you don't need to. Look at how the notation here is. The -1 is separate from the a sub n, and it only has the a sub n here, right? So I'm going to just ignore the -1 and just make this n over 2n minus 1. And let's take that limit. Well, as n goes to infinity, the -1 down here, the -1 does not matter, and I'm left with n over 2n, which reduces to 1/2, right? So this thing goes to 1/2. The limit is 1/2, which is not 0. So I don't have to go any further. This series diverges by nth term test. Don't have to do any more. Okay? Let's look at this one. This is our alternating harmonic series again, right? Let's do the alternating series test on it. So step 1, is it alternating? And a lot of times I will abbreviate that just ALT. It's alternating. Yes, it is. -1 to the n makes it alternate. It's beginning negative, but that's okay, whatever. It's still alternating in sign. The terms are alternating in sign. Okay, is the limit, if we ignore the -1, is the limit 0? Sure is, because this goes 1 over something going to infinity, goes to 0. Check. Step 3. Is the magnitude of the terms decreasing? Is this a decreasing sequence? Okay. Look at the way it's worded up here. Is this true? Is every term less than the term in front of it? This is my test that I'm going to use to prove if it's actually decreasing. So I'm going to replace, again, ignore the -1, replace the remaining n's with n+1, and we're doing a little test here again. Is that less than 1 over n? Well, this denominator is larger than this denominator, and their numerators are the same, so yes, that fraction is less than 1 over n. So this this means the terms are decreasing in magnitude, okay? If you can check all those things, then the series converges by alternating series test. I'm going to abbreviate that alt series test. Very good. Next up, is it alternating? It sure is. It's alternating. Check. Step 2, is the limit 0? Is the limit as n goes to infinity of, ignore the -1, is that 0? Yes, this is going to 0. Check. Is it decreasing? replace n with n plus 1 and compare it to the nth term. Can I put a less than sign in there? Yeah, because this denominator again is larger than this denominator and the numerators are the same, so that is less than. Check. Converges by alternating series test. And that's the alternating series test. Okay? All right, let me go back to my little scratch sheet. Here. Let's take a look at this. The sum of 1 over n squared, and I think I'll start at 1 again, like that. Let's take a look at this series, okay? We know that this is a converging p series, right? This is a converging p series. P is 2, yes? Okay? That means if we started out, we'd be starting out our series of partial sums here. We'd start out at 1, because when I put 1 in for n, I get 1. Then I'd be adding 1 over 4. I'd be adding 1/4. And then I would be adding 1 over 9, right? I'd be adding a 9th. And then I'd be adding 1 over 16. And then 1 over 25. And then 1 over 36. Do you see how this is, yes, it's increasing, and it will increase for a long, long time, but it's increasing such a teeny tiny amount that it is converging. I know it converges. I know it converges. I can do the integral test to prove it, but it is a converging p series, right? If I did the integral from 1 to infinity, that would converge as well, even though it represents the area under that curve that looks infinite because that curve never reached the x-axis, but it's not infinite, it's actually a number, right? So that's that one. So that converged. So what do you think this one would do? What do you think? If this converges, what would the alternating version of it do? Well, I don't even need to do anything on this one. I know that even without the -1, even without the alternating, this converges, right? So definitely with the -1, we're going to converge. Definitely. In fact, absolutely. It absolutely converges, right? If the non-alternating converges, then the alternating version of it will absolutely converge. And that's a term. That's a term. That absolutely converging is a term describing an alternating series, only an alternating series. A non-alternating, it doesn't absolutely or conditionally converge, okay? But what if we have our harmonic? Our harmonic is a diverging. We know that that's a diverging p series or harmonic series, right? But we found out that this one, we found out in example 2 that converges by alternating series test. So in this case, the non-alternating diverged, but the alternating version of it converged. We call this conditional. Conditional convergence, or converges conditionally, either one. So the key word there is the conditional. Actually, the key word is converging. The conditional or the absolute just describes the conversion, the convergence, sorry. Okay? That's the difference between conditional convergence and absolute convergence. So, if the non-alternating converges, then the alternating converges absolutely. Okay? If the non-alternating diverges and the alternating converges, then the alternating converges conditionally. So I always like to check the non-alternating first. Usually you can eyeball that, okay? It's usually a p-series or geo-series, something really obvious. See if that converges or diverges. If it converges, you're done. You don't have to do anything else. If it diverges, then go ahead and check the alternating one and see if it converges. Because if the non-alternating diverges, then the alternating might diverge as well. And if that's the case, then the alternating just diverges. It doesn't converge at all, right? If it diverges, it diverges. So that's the difference between converging conditionally and absolutely. Okay? Let's do an example. I threw in the 3 in here just to show you that it could be in here. This 3 is not to an n power. It's not 3 times n. It's just a 3 sitting there. If a 3 or any number is just sitting there without any n on it, it could come totally out of the sum. It does not affect convergence or divergence at all. So we could totally bring it out. So I'm really kind of ignoring that 3. Okay? So let's take a look at the non-alternating version. The non-alternating version. So that would be like 3 times 1 over 2 to the n. What does that do? Well, it's a geoseries where r is 1/2, because I could write this as 1/2 all to the n power. So this converges because I put my absolute values in the wrong place. R is just a half. The absolute value of R is less than 1, right? So this non-alternating converges. So this alternating converges absolutely. I don't need to do anything else. Okay? What about this one? Well, once again, the 3, I just stuck it in there just to show you that it could be there, but we're not even going to think about that. So I can pull that totally out. So I'm going to examine the non-alternating version first. So this -1 to the n, I'm just going to make it a 1 over the 4th root of n. What does that do? Well, this is our 4th root of n, not nth root of n. Okay, 4th root of n. This is our diverging p-series. P is a 4th, right? A 4th is less than 1. So that's a diverging p-series. So since it diverges, I need to go back and see, oh, okay, I better go through my steps here. Is it alternating in sign? Yes. Is the limit 0? I can keep the 3 up there if you like. Is the limit 0? Yes. Is it decreasing in magnitude? Let me come over here. 3 over the 4th root of n plus 1. Is that less than 3 over the 4th root of n? Yes, because the numerators are the same and the denominators, the left denominator is larger than the right denominator, so this is going to be less than. Check. So this one converges conditionally because the non-alternating diverged, but the alternating converged. Okay? Very good. So far, students usually really like this alternating series test. It's not a problem. Okay. Now I'd like to grab another piece of scratch paper before I get to your notes page again. And grab another piece of scratch paper here. Okay. Okay, let's just talk about something for a moment. Let's say that we have some series. So we have some series, and we know that you can write the terms of the series, whatever they are, and it would keep on going forever and ever, right? Yeah. Okay. Now we also know that if you can add these up, we would get a number, right? So if this series converges, we get a number. We get a number. And we're going to call that number S. So we could write our series three different ways, like this, or like that. They mean the same thing. If it converges, right, to some S, right? We also know that we can write partial sums. We did that when we were first taking a look at series. So, for instance, S sub 3 would be the sum of the first three terms. In this case, the first three terms are right here. Okay? That would be the first three terms. We could write the sum of the first five terms, and in this case, for this one, where n starts at 0, the first five terms would be right here. Okay? So, if you did find the sum of the first three terms, then do you agree that there would be a remainder if you subtracted this from S? What would you get? So in other words, if I took S and I subtracted S sub 3 from it, what would I have left? What would be remaining? Well, that would be everything outside of A sub 2, so that would be A sub 3 in this case, plus A sub 4, plus A sub 5, plus A sub 6, plus dot, dot, dot. We call this something. We call this the remainder. This is the remainder after using the first three terms, so the notation would be like that. That's called the remainder after we use the first three terms in a partial sum. Okay? I'm just talking about notation first before we get into what these things really mean, all right, or what we can do with them. I'm just talking notation. So S with no subscript is our actual infinite sum. Infinite sum. And S with a subscript is a partial sum. Those are partial sums. We can use a partial sum to approximate an infinite sum. Okay? They can approximate an infinite sum. So I did it when n started at 0. What if n started at 1? If n started at 1, then our first term would be A sub 1, and then A sub 2, A sub 3, A sub 4, etc. Right? This whole thing, the infinite sum would be S. S sub 3 in this case would be A sub 1 plus A sub 2 plus A sub 3. The remainder after using the first three terms would be A sub 4 plus A sub 5 plus A sub 6 plus dot, dot, dot. Right? That would be the remainder. Okay, another terminology here, the error. The error, actually the absolute value of the error, because we like for error to be always positive. The error is just the absolute value of the remainder, which is the absolute value, remember, it's the absolute value of the actual sum minus your partial sum. Okay? Or you could write that as the partial sum minus the actual sum, because since we're in absolute values, those mean the same thing, right? So when we talk about error, we're just talking about the absolute value of the difference between the actual sum and the partial sum. This is our approximation. Okay? All right, so let's take a look at our nice friend, our alternating harmonic, which now we know it converges, right? So the first term was 1 minus 1/2 plus 1/3 minus 1/4, etc. Okay. What if I said, okay, I know it converges. I know it converges. It converges by alternating series test. And it's also the alternating harmonic series. So now we can just say it's the converging alternating harmonic series. Okay? So I know that this is equal to some number. I know it is. Okay? Let's approximate it using the first 4 terms. Let's approximate this using the first 4 terms. So the sum of the first 4 terms would be this. And I could, and I think I will, just for the sake of introducing this to you, I could and I will go in and actually find a number for this. So 1 minus 1/2 plus 1/3 minus 1/4, and there is my approximation. And I think I'm going to give you the approximation to actually 5 decimal places now. But it's clear that that's a repeating decimal in this case. Okay? All right. That's the actual sum. That's the approximated sum. My question is, how good of a sum is that? How good of an approximation is that? This is just my approximation for S, for the whole thing. Okay? The remainder here, you guys, the remainder would be 1/5 minus 1/6 plus 1/7 minus 1/8, and I would have to keep on going. So I'm not going to be able to type that into my calculator because it keeps on going, right? But that's my remainder. Look at our remainder. Do you agree that it's another alternating series? Do you agree that? It always will be. If we start off alternating, then the remainder will definitely be alternating still. So this also converges to some number, and it converges to this remainder. This converges. What can I say about it? Well, same thing I said before. Whatever this first number is, I know that this value must be less than 1/5. It has to be, because again, with the number line thing, if I'm starting at 1/5, and then I subtract 1/6, and then I add 1/7, and then I subtract 1/8, and then I add 1/9, I'm going to be less than 1/5, right? It's always going to be, if this is positive, and we're alternating and decreasing in magnitude to 0, then this entire thing is always going to be less than this first term. If it's positive. If it was negative, it would be larger than that, but the magnitude would always be less than. The magnitude of it would always be less than it. Okay? For instance, what if I had just changed all the signs? Negative 1/5 plus 1/6 minus 1/7 plus 1/8, etc. So here I am down here at negative 1/5, right? And I'm going to add 1/6, subtract 1/7, add 1/8, subtract 1/9, etc. Right? So what we have found out is that in an alternating series that is converging, the remainder, which is, this is the error, another way to write the error. The error is always less than your first omitted term. The error in an approximation, whatever your approximation is, the error is always less than your first omitted term, the absolute value of your first omitted term. Okay? So that's what all this says. So first of all, it has to be converging alternating series. It has to be, for us to use the alternating series remainder theorem. Okay? And if it is, then the error in an approximation, this S sub n is our approximation, is always less than or equal to that first, the absolute value of the first omitted or unused term. Okay? Let's look at an example. And it has to be alternating in sign. That's our step 1, right? Step 1. Decreasing in magnitude, that was our step 3 actually. To 0, that was our step 2. The limit was 0. Okay? We can say this in words, or you can write it in math symbols like we did in our examples, first 3 examples here today. Okay? Example 1. Approximate the sum, the infinite sum of this series by using its first 4 terms. Okay, I can do that. I'm going to write out the first 4 terms, and I'm going to call this S sub 4 because it is the first 4 terms. So S sub 4 would be, okay, what is our first term? Take your time and plug in this number in for n. When I plug in that number in for n, I get 0 here. Negative 1 to the 0 is positive 1, so it's positive 1 over 1 factorial, right? Our next term is when n is 2. When n is 2, negative 1 to the first is negative 1. And I have 2 factorial plus 3, negative 1 to the second is positive 1. So positive 1 over 3 factorial minus 1 over 4 factorial, and those are my 4 terms. A common mistake I see kids make: first 4 terms, and they go to when n is 4. In this case, that was accurate because n started at 1, but if n starts at 0 and you're given the first, and you are giving the first 4 terms, you'll only go to when n is 3 if n starts at 0. What if n started at 3? Then the first 4 terms would be when n is 3, 4, 5, and 6. So you always want to count the terms and make sure you're making them correct. This would be a safe stop spot, but I'm going to go ahead, just for the sake of notes, I'm going to go ahead and find out what this is as a decimal, an approximation. So this is 1 minus 1 over 2 factorial. 2 factorial is 2, plus 1 over 3 factorial. 3 factorial is 6, minus 1 over 4 factorial, which is 24. So this gives us 0.625. Okay? So that's our approximation. Explain why your estimate differs from the actual value. Remember, the actual value is S with no subscript. Why your estimate, that's our S sub 4, differs from the actual value by less than 1/100th. Okay? Well, I'm using this alternating series remainder theorem, but I cannot use it without stating why I can use it. And the only reason I can use it is because the terms in the series alternate in sign and decrease in magnitude to 0. Okay? When we're in class, I have you guys in class repeat this a few times. The terms alternate in sign and decrease in magnitude to 0. We say that several times. So if you want to turn off your video and say that a few times, it might help you remember it. Magnitude just means absolute value. It means if we ignore the negatives, if we ignore the alternating aspect of this, then the terms will decrease in that value. Okay? So this is true for this series, which means, therefore, the error is less than the first, you can say omitted or unused, whatever one you like, the first unused term, absolute value of the first unused term, because sometimes it'll be negative, right? So the absolute value of the error is less than the absolute value of the first unused term, right? So since they gave it to me, they asked me why my estimate differs than the actual value, I'm going to do this. My estimate differs from the actual value by less than. Some textbooks use an equal to sign here, and some textbooks use a less than. Some textbooks say less than or equal to, and some just say less than. I'm going with what our textbook says, which is less than or equal to, okay? FYI. But if you do the other way, AP accepts that also, okay? All right. Less than or equal to, what is the absolute value of our first unused term? What was our first unused term here? We went up to 1 over 4 factorial, which means our first unused term would be positive 1 over 5 factorial, right? Well, 5 factorial is 120, and that is less than 1 over 100, which is what we were trying to show or explain. So that's it. That's that one. Not too bad. Hopefully it makes sense. Hopefully it makes sense. Now we're going to use the results here to find an interval in which S must lie. So even though we cannot find the actual sum, we're finding an interval in which the actual sum must lie. Okay? So here I have what I showed here. I'm going to pull this out again. So I have the absolute value of S minus S sub 4 is less than or equal to 1 over 120. I know that that's true. Now, get another scratch sheet of paper. When you have the absolute value of X is less than something, what can X be? Can X be 20? No. Can X be negative 20? No. Can X be negative 2? Yes. Can X be positive 2? Yes. X is anything between negative 7 and 7. These mean the same things, right? This is an absolute value form. This is an interval. We want to find an interval in which S must lie. So let's change this out of absolute value form and into interval form. Okay? So S minus S sub 4 must be between the positive and negative of whatever is here. So negative 1 over 120 and positive 1 over 120. And now to get S by itself in the interval, I'm just going to add S sub 4 to all 3 parts. So I'm going to get S sub 4 minus 1 over 120 and S sub 4 plus 1 over 120. Okay? Now let's go ahead and find some numbers. So I'm going to grab my calculator. This was my S sub 4, right? So I have S sub 4 and I'm going to subtract 1 over 120. So that is, and I'm going to give 5 decimal places again. Okay? And then S sub 4 plus 1 over 120. So 0.63333. Okay? So even though we only used 4 terms in the approximation, look what a great approximation for the actual infinite sum that was. That's a pretty close, that's a pretty tight sum for only using 4 terms. If we had used another term, our error would be 1 over 720. And so this would have shrunk significantly, right? We'd be adding and subtracting 1 over 720 instead of 1 over 120. Okay? All right, number 2. What is the fewest number of terms required to approximate the sum of this series so that the estimate differs from the actual sum by less than 1 over 1,000? Okay, let's write out some terms. Let's write out some terms. So I'm going to write out some terms. Go ahead and write this out. Starting when n is 1, our exponent is even, so we're going to start positive. 1 over 1 to the 4th is just 1. Plus, I'm sorry, minus, because our next one will be a negative, right? 1 over 2 to the 4th. 2 to the 4th. What is 2 to, well, I'm going to write 2 to the 4th right now. Plus 1 over 3 to the 4th. Minus 1 over 4 to the 4th. Plus 1 over 5 to the 4th, minus 1 over 6 to the 4th, plus dot, 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 and we would keep on going, and that is our actual sum. That's our actual sum, right? What do you notice about the terms? The terms are alternating in sign. You can abbreviate. They're alternating in sign and decreasing in magnitude. You can abbreviate for me. If it's AP, write it out. Decreasing in magnitude to 0. So the error in a the absolute value of the error of a partial sum is less than or equal to the absolute value of the first omitted or unused term, right? So let's take a look at these again, and this time I need some values because I want for my error to be less than 1 over 1,000. I want for my error to be less than 1 over 1,000. Which means I want my first unused term, to be less than 1 over 1,000, right? So let's write out some terms. Well, 1 is definitely not less than 1 over 1,000. 2 to the 4th. What's 2 to the 4th? 2 to the 4th is 16. Oops, 2. 1/16. Okay, 3 to the 4th. What is 3 to the 4th? This is where in class I usually have a student who can spit these out to me. 3 to the 4th I know is 81. Okay, what is 4 to the 4th? And I would say, does anybody know what 4 to the 4th is? And usually there is somebody who knows it. It's 256. 5 to the 4th is one that I know. It's 625. Well, I'm keeping in mind, I'm trying to get to 1,000, right? What is 6 to the 4th? 6 to the 4th is one I don't know off the top of my hand, but it is 1 over, it would be this, it would be much higher than this, right? So 6 to the 4th is 1,296. I get to stop because I found a term, I reached a term that was less than 1 over 1,000, right? The denominator is larger than this denominator, their numerators are the same, so I'm there, I am there. So that means this is my what I would put in right here. That would go right here. That's my first unused term. It's my first omitted term. And I say that because I'm about to ask you a question. How many terms should I use? Because what is the fewest number of terms required to approximate? How many terms should I use in my partial sum then? If this is my first unused term? 5. I need to use 5 terms. This is my first unused term. I'm stressing this because you can guess why. Kids, they get here and they know to stop. They know to stop there because they found one that was less than 1 over 1,000, but then they proceed to use it as one of their terms in the approximation. And this was the first unused term, not the last used term, right? So do not use this one in your partial sum. This is your partial sum. So we would be needing, not P, S sub 5 here. That would be our partial sum. And then this would be our unused one. Okay? All right. This is one of my favorites. I love this section. I find it it's interesting. I like what we can do with it. I like the meaning of it, and I like that it's really meaty. We're doing a lot of conceptual stuff, but it also has a little meat in it. We get to get out our calculator and find some ranges, and it's just fun. It's fun to do. So time for you to go practice. So go practice and ask me questions when you find them.